Yeah, in the last class, we have discussed on the spur gear problem, in which the spur gear is a diameter unknown problem. Okay, today I'm taking an example of diameter known problem. Go through the problem. A air compressor which is as a power of 20 kilonewton motor through a pair of 14.5 degree involutes per gear. In the last problem, they had taken 20-degree full depth involute system. Okay, the tooth formation has changed in this problem. Okay. Next is the speed of the compressor is given as 300 and the center distance is approximately 400 mm. The center distance between the pinion and gear. Okay, that distance they had given as 400 mm. By using these center distance, we can find the diameter here. Okay, so that's why this problem, what we call it as a diameter known problem. And the type of material is given, that is pinion is cast steel untreated and gear is cast iron grade 3 grade 35. Okay, by using these type of materials, we can find the allowable stresses of the material. Okay, next, assume the gear are subjected to medium shock. In the last problem, we have assumed these things, that working condition, to select the service factor CS value. Okay, here they only mentioned that 8 to 10 hours duty per day, and they ask you to design the gears and check for wear load. This is what they asked in the problem. Okay, next, write down the data, that is alpha is nothing but the tooth formation and power. Okay, those things are given, and based on the type of material what they had given, we can get the allowable stresses of the materials from table 12.7, page number 186. For cast steel material, allowable stress is 138.3, and cast iron grade 35, allowable stress is 56.4 megapascal. Okay, here for pinion as well as gear, we are using the different type of materials. In the last problem, we have used the same material for both the pinion and gear, but here the thing is changed. Okay, next, here the procedure is almost similar with what we have done in the last problem. Here also, thus mainly there you have three steps. Then the first step, we have to decide which one is the weaker member, whether the pinion or the gear. There is a first step. And then in the second step, we are finding the module M. Okay. In the last third step, we are checking for the stresses. That is the dynamic strength and wear strength are the checking for the stresses. Those are the three steps what we are dealing here. Okay, first is, as you know, that velocity ratio I is equal to n1 by n2, z2 by z1. These things given because the speed of the pinion as well as speed of the gear is given. That is 1200 by 300. That will give the value for I is equal to 4. Okay. Next, once we have that velocity ratio I is equal to 4. Next, the center distance in the problem is given here. That is through a pair of involute gears, and that center distance as 400 mm here given. The center distance is approximately 400 mm. By using these 400 mm, we can find the center distance. That is center distance C is equal to d1 plus d2 by 2. This is an equation. Okay. And by this relation, velocity ratio I is equal to, I can write it as d2 by d1. So that will give that d2 is equal to I into d1. Okay, this is a condition what we'll get from here. Substitute here, only the unknown variable here is d1. So by substituting, I can get the value for d1 as 160 mm. Once I have that value for 160 mm, by substituting in the velocity ratio condition, I can get the value for d2 as I into d1, that is 640 millimeter. So what I find it here is the value for d1 as well as d2. In this case, the z1 and z2 are the two unknown parameters. Okay. Next, the first step is important step is identification of the weaker member. To identify the weaker member, we have to use the Levi's form factor. That is a Y equation from table from page number 163. There we have three equation 12.17a, 17b, and 17c. That is one for 14.5 degree, and another is for 20 degree, and another is for 20 degree involute system are the three equations we have. In the last problem, we have used with 12.17b equation, but here they had mentioned it is a 14.5 degree involute system. So we have to go with 12.17a equation. And here equation is given here, y is equal to 0.124 minus 0.684 divided by z. Z indicates the number of teeth here. Okay, in this problem, both the teeth for pinion and gears are not given. So what we have to do, only for this identification of the weaker member purpose, we are not using these, whatever the t's I'm assuming here for my further calculation. Only to identify the weaker member, I am assuming that Z1 has 20 number of teeth. That is the pinion teeth as 20. Once its pinion is 20, you know that ratio distance between pinion and gear, that is 1:4. Once you assumed it's as 20, automatically the Z2 will be 80 because 1:4 ratio. Okay. So by using that assumption, I'm taking as Z1 as 20 teeth and Z2 as 80 teeth. Okay. And substituting in the above equation 12.17a, I will get y1 is equal to this value as well as y2 as is equal to this is a value. Okay. The same procedure, I have to draw the tabular column and substitute that sigma d into y. Once I substitute in both the conditions, out of these two, gear is the weaker member because for pinion it is 12.42 is the value and for gear it is a 6.51. Okay, by looking onto these values, we can decide which one is the weaker member. The design should be based on the weaker member. The thing already you know. So what we have to conclude is design should be based on the weaker member. That is the gear here. That means 2. Okay, that's the first step is completed. The second step, we have to find the module M. For that module M, first we have to use the general tangential equation, that is IFT is equal to 100 CS, 100 P into CS divided by V. P indicates that power is given here, in this case 20 kilowatt. CS is a service factor. That service factor is related data is type of load, that is the medium shock 8 to 10 hours duty per day. This is also mentioned in our problem. And the next thing is V is velocity. We have the equation pi dn by 60,000. This is the equation what we have. And here in this case, already I have that value for diameter D1 as well as D2. Here I have to use D2 because the design is based on the gear. 2 indicates gear, 1 indicates pinion in our problem. Substitute all the things in this equation. Ft is equal to 1000 P CS divided by velocity V. V is equal to pi dn by 60,000. Okay. And substitute here so that I will get Ft is equal to 2984.2 is the value. In the diameter unknown problem, we are getting in the denominator value M. Here we don't get any module because I have directly substitute the value for diameter, not used this D is equal to MZ condition. This is the general equation I had used. And the next step, we have to use the tangential equation which is given by Levi's, that is Ft is equal to sigma d Cv dy into M. This is the equation 12.15. This is what given by Levi's. Substitute this equation here, sigma d Cv by2 into M. The 2 indicates the design is based on the gear here. In the previous case, we have used sigma d1, cv1 as well as y1. That indicates the design is based on the pinion in the previous case. Okay. And sigma d is allowable stress value is known, that is 55 megapascal, and cv keep as it is. B is the phase width. You know that already we have used that phase width. That range is in between 9.5 to 12.5. You can opt any of the value. You can opt even the 10 times of module or 11 types of module. Both the things are acceptable here. Next, Y is the Levi's factor, pi into Y, and M is the module. That is the unknown parameter. And even I have the velocity V2 also. Once you have that velocity V2 value, by using this velocity V2, I can decide the which equation I have to use for velocity factor CV. Based on velocity range, we will decide the equation. Once velocity is lesser than 8 meter per second, then we'll go with 12.19b. Here, velocity is lesser than or equal to 13 meter per second square. That's why I have to go with 12.19. Yeah, that you can see here. Velocity is 10.053. So we can use this equation 4.58 divided by 4.58 plus V2 velocity. Substitute the values in the above equation and you are getting as CV is equal to 0.313. Once you have that value for CV, just mainly you have to substitute in the main equation. This is what required. Next thing is substituting for y1 and y2 or the Levi's form factor. Okay, here in the previous itself we have substituted one value for y2. That means 0.124 minus 0.684 divided by 80 I had used it. Okay, that is only assumed value, that not an exact value. Okay, that 80 is only for the deciding of the which one is the weaker member. We can't use that value here for our module calculation. We know that relation D is equal to mz. Okay, so that will give that z is equal to d by m, that is d2 by m. With this relation, we know that d is equal to mz. By that relation, we can substitute here z is equal to d by m. Substitute the values here. D value is known, only the unknown value remains is m value, and substitute y2 as it is in terms of module m. Finally, I'll get FT2 is equal to 554.6 into m square into y2. This is the equation 2. In the same manner with the previous problem, here also I have to equate equation 1 and equation 2. While equating these two things, I will get m square y2 should be greater than or equal to 5.38. This is the required equation. In the previous unknown problem, we are getting as m cube CV should be greater than or equal to certain value. In the diameter known problem, we are getting m square y should be greater than or equal to certain value. This is a difference you have to notice with the diameter known problem and diameter unknown problem. Okay, this will remain same for diameter known and unknown problems. Next, we have to decide the what is the value for module m. That we have to do by trial and error method. First, for the first trial, I have selected module m is equal to 5 and substituted that module m in the equation of y2. That will give y2 as 0.11866. Once I have that value for y2, substitute in the equation 3 here. Okay, that I will get 2.9665, which is lesser than 5.38. So that condition is not suitable. So I will go with the another condition, that is m is second trial, m is equal to 6. Once again, I got as 4.233 is which is lesser than 5.38. So this condition is also not acceptable. Go for the third option, m module m is equal to 7. So that will give that value as 5.7095, which is greater than 5.38. So the condition is satisfied in the trial number 3. So I have to select module m is equal to 7 here. Once I have that value for m, I can find the face width b is equal to 10 times of module, that is 70. And once you have that value for module m, I can draw all the dimensional parameters of the gear like addendum, dedendum that we mentions as HA, HF, number of teeth, Z, and the circular pitch diameter. Those things you can plot in the tabular column. The next step is check for stresses. We have to check for both the allowable as well as induced stresses. Here in this case, the allowable stress of the given gear material will take it as sigma d into CV is that which is nothing but the velocity factor. The allowable stress of the working stress of the given material as 56.4 megapascal into 0.33 is the velocity factor. Substitute here, that will give the value of 17.65 megapascal. This is allowable stress value. Next, check for induced stress value. That equation you can extract from equation 12.515. That is the Levi's equation which they had given for tangential tooth load. Here substitute Ft to By as well as M here, and you'll get that value as 16.64 megapascal. Now comparing with the allowable stress and the induced strength, allowable is 17 and induced is 16.6. So we can conclude that induced stress is lesser than the allowable stress, hence the design is satisfactory. Okay, that is a one stage in this step number 3. Next is the checking for the dynamic load. That equation we have 12.33 for the spur gear. Under this equation, FD is the known value. That is a general equation what you will get. And K3 value is known. That's a 20.67, which is given below the equation. And velocity is known. B is known. Only the unknown parameter is C. That is a dynamic factor. C value I have to find here. To finding that value for C, I have to use the two tabular columns. One is table 12.13 and table 12.12 are the two equation. So two tabular column I have to use. First from table 12.13 for the respective value of module 7 and carefully cut gear, the value for machining error is 0.0353. This will be the value I can get from table 12.13 from your data handbook. Once I have that value for 0.0353 is the machining error, the respective value I have to check from the table 12.12. For that each machining error value, the dynamic factor values are given from table 12.12. In this table, there you have that machining error value for 0.03 is 227.4 and for 0.04 is 343.5 are the two values I have. But in our tabular column, I don't have the exact value for 0.0353. To get the 0.353 value, I have to go with the interpolation. Or either you can use that cross multiplication condition, because we are not getting the exact accurate value here in the cross multiplication, but almost the nearer value I can get from that cross multiplication. Okay, that is C into 0.003 into 227 into 0.03353. By this cross multiplication, I will get that 267.574 megapascal is the dynamic factor value for the respective value of 0.0353. Okay. Now substitute all these values in this above equation 12.33, and after substitution and simplification, I will get as FD is equal to 15689.2 Newton is the dynamic strength of the gear material. Okay. Next, in the same way, I have to go with the next step is check for wear load. That Buckingham's also they had given an equation for wear load as Fw is equal to D1 BQK. Here D1 is the diameter and B is the face width and Q is the ratio factor. Okay, and K is the load stress factor. For this Q and K, I have that equation. Using those equation, I have to get an value here. The first thing is the Q, that is a ratio factor. This is nothing but 2D2 divided by D2 plus D1 or Z2 by Z2 plus Z1. You can use any of the equation because both the things are known here. D2 is also known as well as Z2 is also known here. And there I have that value Q is equal to 1.6 is the ratio factor. The next thing is I have to go with K, load stress factor. Before going for the load stress factor, I have to check for the Brinell hardness number for the pinion as well as gear material. Here the type of material is given, that is a cast steel for pinion and cast iron for gear material. From table 12.7, page number 186, the respective values for pinion and gear are 180 and 225 are the Brinell hardness number. For pinion it is 180 and for gear it is 225 is the Brinell hardness number. For this condition, I will take an average of these two Brinell hardness numbers. That will give 202.5 Brinell hardness number BHN. Okay. Next, for the given type of material, even we can get the Young's modulus of the material from table 1.1, page number 7. For cast steel, it is 202 gigapascal, and for cast iron, 100 gigapascal. These are the Young's modulus for the material. Next step, that is end surface endurance limit equation 12.36d. We have to substitute the Brinell hardness number here. By substituting the Brinell hardness number, the endurance stress is 486.875 megapascal is the value for endurance surface limit. Next, substitute that endurance surface limit in the load stress factor equation. That is K is equal to this equation using the modulus of elasticity for both the materials, for pinion as well as gear, that I can get from equation 12.36b. Substitute here, alpha indicates that 14.5-degree involute form, and sigma E square is 486.875. Substitute and get a value for K. K is equal to 0.336338. Once you have that value for Q and K, substitute in the above equation so that you will get FW, that is a wear load, as 11357.7 Newton is the value what you are getting for wear load. Now comparing with that wear load and the dynamic load, which one is the maximum here is the dynamic load. Okay, so that by this point of view, the design is not satisfactory. For the safe design, what we required is that wear load should be greater than or equal to dynamic load. This is a condition what I required, but that condition has not satisfied here. Here in this case, that wear load FD is greater than FW, but what I required is FW should be greater than FD. So what I have to do is just write down the one conclusion here, that is the design is unsatisfactory. Next, for safe design, what we have to do is, what you required is FW should be greater than FD. Substitute the value for FD here, that is 15689.2, and equation of wear load FW. Keep K as the unknown parameter, D1 as it is, B70, Q 1.6, and K keep as it is as the unknown parameter. And by simplification, I will get K should be greater than or equal to 0.8755. This is what the condition required. But what I have is K is equal to 0.633. This is what I get from the calculation. But what I required is K should be greater than 0.875 megapascal. Okay. By taking this value from table 12.16 from page number 193, I can suggest the preferable Brinell hardness number for pinion, that is cast steel material, and for gear, that is for the cast iron material. So which is the preferable suggested material for pinion has to contain Brinell hardness number of 250, and for the cast iron gear material as 180 Brinell hardness number. Once the materials are having this Brinell hardness number, the design will be satisfactory from the point of wear as well as durability. That is how you have to conclude the diameter known problem. There is a difference between diameter known problem as well as the diameter unknown problem. Only the main difference you have to notice here is, in the previous case, we are getting the equation 3 in terms of m cube CV should be greater than certain value. But here, m square y should be greater than or equal to certain value. Only those two difference you have to notice in the diameter known problem as well as diameter unknown